Hello guys and girls, and welcome back to my YouTube channel, where today I'm going to be explaining to you guys about priority queue homework. So, first off, let's look at his homework. What are we making with Dr. Sweller this lovely evening? Pretty simple assignment if I don't say it myself. So, okay, we're making a min priority queue. That's pretty fascinating. So, we have a couple functions that we have to do. Constructor, size, push, front, pop, and decrease key. So let's go over these functions right now. So first of all, let's go over the easy ones. So let me get my I just lost my notes. Alright, here they are. There we go. Where's the PowerPoints here? Alright, there we go. So let's first check if my pen is working. Let's go to the first slide and check that. So in today's color, I'm going to be using, let's go with a little bit of darkish blue. Let's test that out. Okay, that's a highlighter. Darkish blue. And let's erase this. Let's test it out again. Alright. That seems to be working fine. Alright, so first of all, let's work on the constructor, size, and front. So the constructor is pretty simple one. We have this vector called h. And all we're doing in the constructor is just clearing h. Alright, so if my mouse, if my little my little pen isn't working right now, I'm gonna be doing everything by hand like usual. So we have this there's a vector that has a pair of t and int, which is your heap of h. Well, all we want to do in the constructor is just clear the information, just in case it has something. You never know. That's just for precautions. Size, it's a very simple function. You just return the size of h. Now, front, also simple function. Now, what you have to keep in mind about this h is that it has a pair. The type of data input that it has, it's a pair. So it has t and int, where int is the priority, and front is basically telling us that we want to return an item, the very front item. So all you're going to do is going to do h.front. Or first, sorry. h.first. h.first at 0, you know, because it's a vector and you want to get the first item from this location. And that's mostly it for these functions. It's fairly simple. Anyone, Dr. Schuller teaches you these methods that you're going to be using, like front and all that. So let's go on to the second problem, which is what I recommend is creating helper functions. So if you guys don't know what you guys are doing, so let me see if I can, grab his PowerPoints. What I really recommend is, I believe it's this one, where it showcases the priority. Yeah, like push, pop, front, size. It's mostly what you're going to be talking about. And there's a portion here about the math. Well, I'm not going to do it right now. I'm not going to do the math right now. Look for the math. I'm just going to explain it to you guys. So what we know about this is that we have this sort of tree-looking thing, or heap. So it looks like this. Now, can you guys give me a guess of what's the parent, what's the left and right child? Well, it's pretty simple. This will be your parent. This will be your left child. And this will be your right. Oh my god, my handwriting is pretty horrible. So, how we're going to use this, this knowledge of left, parent, left, right, all of that is that we're going to be using a vector for it. So this vector is going to look like this. And let's say I have this item, which is my, is just 1, 2, 3. Now 1 is right here in this location, 2, and 3. Now, how do I know where to get my parent? Well, parent is always located on a certain index. So, for example, let's say I'm at this index. If my mouse will be working and cooperating. Okay. It's gonna be... Okay. I'm just gonna use this. It's gonna be located in this index. And let's say this is index 0, 1. So 1 minus 1 divided by 2 is equal to 0. So this will be 0. Now what I did is I'm in this child location and I want to find my parent. So what would you do? The equation for this helper function, the parent, would be index minus 1 parentheses divided by 2. So this would help you for the parent function. Now let's say I am the parent and I want to look for my child. So what I would do is basically my left child, which is this one, I'm gonna be multiplying my parent index by 2 plus 1. So 2 times index plus 1. And so let's say here, so 0 times 2 plus 1, oh, it's 1. So that's my left child. And for my right child, it's going to be something similar to this by doing 2 times index plus 2. So this is going to give me 2. The main reason I am telling you guys about these helper functions is because I've noticed a couple students are kind of didn't implement this correctly, so it might cause an error. So that's it for the helper functions. Now,
what was the 2 times the index plus 2 for? That's to get the right child?
Yes.
And to get the left child is just 1? And that's going to be the case every single time?
Yes, it's always going to be the case for every single time.
Even if we're like, already have like 4 children, or, I don't know, even more children than that, you can always still use the, its index?
Yes.
Okay.
So if you're a parent, so for example, let's say 3 is a parent, and I look at I want to look for my right child. I implement the current index at 3, which is 2. So 2 times 2, that's 4, plus 2 is 6. So my right child, I believe it's going to be looking like this. My right child is going to be index, wait, I have to fill this out to be, so the data structure is correct. So my right child will be index 6 on this case. 6, this would be 5. I believe this is 4, and this is, wait, did I do this right? Let me see. Yeah. Indexes. So these are indexes that the ones I'm inputting. So 6, 5, 4, and then 3. These are the the values, so the big ones. There's just does that make sense?
Yeah, that makes sense.
All right. So now let's get on to push. So first thing you do a pushback on H. So you want this item, which is push contains a T of X and P, where P is your priority. So you're going to be pushing these elements, X and P, into your heap. For some simplicity, you can also do push I, which is I in this case is going to be keeping track of your indices in H. This is used for your, I believe, decrease key. So you can also do, push I, where I'm using X as my key here, and then the current size of H minus 1. So that's the simple part of this. But then the little complex part that you guys are going to have to do is create the bubble up. So the bubble up works by inputting an index at your current location, which is your h minus size, your h size minus 1. All right. So let me give you guys an illustration of this, just for simplicity. So I have this tree, and I just added a new item right here. So what I would do is first check. All right, let's say this item says this item 5, 3, and then 1, right? No. I need to make this a 5, just to make it a little bit more accurate. So 3, 5. Well, this is gonna do a bubble up, move up. So what would you do in this case? Well, it's quite simple. What we need to know is that we're currently in this node, or in this index. What I need to know is, do I have a parent? So I need to check if I have a parent. And if I do have a parent, I need to check, is my priority for, I believe there's a min priority. Yes. Is my priority less than my parent priority? So in this case, yes. Wait, is this priority less than this priority? Yes. So what would you do is you would swap the indexes, because of, well, you would swap the elements. So I would do a swap on these two elements using my helper functions, which is the parent. Because parent knows if I have a parent. Well, if this child has a parent. Because what happens if I'm in this node and, well, there's no parents? Can't do anything about that. So swap them. And when you swap them, how I do it is via recursion. I just recall bubble up. I recall bubble up and put the parent index. You can also do a while loop where I check if I check for the parent and the children. Does that kind of make sense what I'm trying to explain? Because what I'm trying to explain is the priority. You have to have the priority. So these numbers right here, 3, 5, 1, they're the priority you're going to be working with. And I know that 5 is greater than 1, so the priority of this min heap has to go to 1. So I'm going to be swapping. And once you're at decrease key, you're also going to be swapping the indexes in the unordered map in I. Unordered map of I. So that's mostly just it for bubble up and push. I hope this makes sense. I did mine via recursion. So I basically just recall the function with the index. You can do a similar process using a while loop. I believe Dr. Scholler also teaches this with your algorithms. So that's mostly just it for this function. Does anyone have any questions about this one? Anything unclear?
Okay, so the only things I'm checking is if I have, like when I'm pushing an item, I start at the bottom rightmost node, and then I start bubbling up. But I do that by checking if I have a parent, and then if I check if that parent value is more or less than mine. If he's more than mine, then I get to bubble up and he switches with me, and then you have to keep checking the parents, right?
Yes.
Okay. Anything else to keep track of?
No, that's mostly just it for keeping track of, like, in the bubble up.
And you have to like reattach all the children to the new parent, right?
We have to reattach the. Can you repeat that part?
Yeah, like let's say one switch with 5, but like something else was attached to 5 as well. Would I have to make one point at the other element as its child, or how would that link be made?
Uh, so five here is being swapped with here, right? So this
Yeah,
five,
like
this.
let's say there's 5 and 1, and then like another child, like a right child.
Like, for this guy right here, right? Or do you mean on the
Right.
5?
Yeah, on the 5.
No.
So
Because,
so you want?
the reason for this is because it's, there's never going to be a right child.
Oh, okay, okay.
I heard your implementation that you're inserting at the right side, which, you kind of, I feel like that's incorrect. But you're always inserting on the left side. So, for example, let's say I have this data structure. Where would I insert? Well, I'll start inserting right here. Where would I insert next? Well, right here, right here, right here, until I fill it up, until my parents only have 2 children. So once it fills up, I start pushing here, pushing here, pushing here. So you never reassign the right because there's never a right. For this example, oh wait, yeah. For this example, I just made it look a little bit. I forgot to add this right node, but I inserted on the left. Wait, no, yeah. I never had this right node. I inserted on left like this, and then I swapped, and then swap. That's mostly just it. And then like your parent is what you're gonna be swapping with the most. So this is always gonna be your parent. So right now this is a 1. Right now it's my parent. Now what's gonna be my parent for the next one? Well, this is my parent. Now I use this to bubble up, so I need to use bubble up on this parent because I swap, and this one. That kind of makes sense.
Yeah, that definitely makes sense.
All right. So next one is pop. Okay, I do some fancy stuff with my code here, but let me see if I can explain it to you guys. By fancy stuff, there's something very cool about C++ and every single language, where you can have a if statement in a way without really having a if statement. So it kind of works like this: bool expression, and then I believe it's question mark. Whatever you want here, you can put a Boolean expression or like anything, or int, Boolean, whatever you want, and then you have your colons and do the exact same thing. Boolean expression, int. So I forgot the name for this, but it's very cool. I use it in my implementation. But let me start explaining to you guys what you guys are going to be doing in pop. So first things first in pop is check if the size is 0. Like you have nothing in it. And then how popping works is by doing this. So let me give you guys a visualization. So this is 0. This is my index 1. And let's make I have a tree. I have a tree like this. And then this is my last element. So this is 20 or something. I have to swap my front with my last element. So, and then you do a pop back. You can swap it or just, assign this as 20 and then do a pop back to remove. Well, what we mostly just want to do is remove this node and change this into a 20. And from that point, I'm going to do a bubble down. At my root. Because this number is 20, let's say this is 5. We know that this is incorrect, so we start, bubbling down until it hits its corresponding spot. My god, my pen is not working. So, we understand the logic behind it. Now, let's see how to write it. Now, first thing you need to check is, do I have a left child? How do I check if my index at 0. So for example, right here, I have a left child. So this is my root, or this is any parent. So this is any parent that I'm looking at. Root is going to be a 0. And what I need to check is that, is my array, does it contain more items? So I check the size with the child, my left child, because I always insert it at the left. And let's say, let's do the math here. Let's say I have no items. That's h is 0, and then my left child is 0. Well, let's say h is 1 because size works like that. Well, if I want to look at the left child, I have to do 2 times is it 2 times 1 or is it 2 times 0? There's no items here. 2 times 0 plus 1, that's index 1. Yeah, it's 0. So check the size. If this is 0, less than, let's check, then it's 1 on the child. Child is located at 1. And then compare which one's bigger. Well, I have no items here, and I'm looking at the first child. Well, I have to return because h has 0 items. That's how kind of how it works. That's going to be your your base case. Check if you have the correct items, or check if you have items to keep going through the children. Now, once you have that, you know you have a left child. So you know you have a left child. Now, the second thing is you're going to do something similar, but you have to make sure if you have a right child. So similar process is h greater than my helper function of right at index at my parent index. If it is, then good thing. You have to make sure of 2 things. So left has a priority, and then the right child has a priority. Right child has a priority. Now, and this is like all in H, because right child, left child functions, they return indexes, so you have to put this, in the, you have to, what you're getting is this. And we pop, let's say this is 20, this is 5, and this is 3. I want to get the minimum value from these two. So you can do this in whatever way you want, but whatever your minimum value is, that's what you're going to be swapping with. So in this example, my minimum value here is going to be 3. I swap with 20. So then I check. Hey, is my because in some cases you're going to have this or something. 6 and then 3, 5 or something like this. You might have. I'm not very sure. But what we want to do here is basically assign. We want to work with this child. If it's like the right child that's less, we work with this child. Now, once you know which child you're working with, you're going to have a statement where, hey, is this number greater than this one? Because in some cases, you're going to have like something like this. Now remember, like 21, 22. There's the minimum value. And we want to swap with this one. Oh, but we can't, because 20 is already the minimum value. We have to make sure that we're swapping only the minimum values to the parent. If there's no minimum values that we need to swap, don't swap anything. And similar process, you're going to be swapping the indexes, and you're going to be swapping the whole elements. So just swap these two. And then you run bubble down on the child you worked with. Because you're going to have something funky like this. So let me erase all of this so I can start rewriting it a little bit better. So I'm just gonna write this fast. 3 and then 6. So I swap with this guy. This becomes 3. This becomes 20. Now I need to focus on the child, which is right now I'm in the current index, which is my parent index. Now I need to go to my left child. It does exist, so this turns into a 20. This turns into a 6. I redo it again. There's no child here, so I stop doing it. Alright, does that make sense? Any questions about this one?
Would you recursively call to go down once you find out which branch you have to go down through?
You can do recursions or while loops. They're recommended. Any of them will work.
Okay.
Alright, now for the... Where is it called? Decrease K. Where is it? It's in the... Where is it? Wow. It's in pop... There it is. So let me give you guys an illustration here. If I can. So, if X is the minimum priority with the current at least new P, then change the priority of X to new P, undefined behavior otherwise. So let's see how I can do this. How to explain this. Because what I mostly just do is you have this histogram that keeps track of all the indexes of each key. So key here is going to be your X, and each histogram has an index. So there's going to be your function I, and then you have your H, which you're going to be like, let's say I'm looking for X, and X is located on this index, which is 2. Then I plug it in here, 2, and then I assign it a new pointer, a new priority, I mean. So that's mostly just it. You're just reassigning the priority. But the thing is here that when you're reassigning the priority is that you have to do a bubble up to make sure everything's correct. So let me make this and this. So this 1, 2, 3, 4, 5, 6, 7. Let's make this a 2. Let's make this a 3, and let's make this 3.5. And let's say I do a new priority on this one. So this index 1, 2, 3. This index 2. So at index 2, I bubble up. I want to bubble up. So this is, I'm setting this one as at 1. So I do a bubble up, and they swap. That's mostly just it. Yeah, that's mostly it for this one. It's not that hard. Yeah, it's. So let me explain to you guys.
What was the point of the histogram again?
The point of the histogram is to keep track at where your items are at, because you want to update, let's say, this specific key. So in the tree, or in the heap, let's say I want to update this specific, but I need to recurse through it to find it. Well, I has that information placed for you. So this is key 3, and the index, which is the value, it's going to contain the value of 2, because that's where your location's at. So I keeps track of every single value located inside your H vector or your heap. Now, any questions on decrease key? Any questions in general that you guys still have about the other functions? I can go back. Alright, so no questions at all. So I'm going to end the video right now. So thank you guys for watching. Hit that like and subscribe button, and see you guys next time.